Okay, so now we're going to look at a topic called implicit differentiation. This may be one of the most confusing topics initially for us, okay, that we've seen so far. It's very doable and it's actually fairly mechanical. It's really just an application of the chain rule, but it's going to feel a little bit weird at first. So just bear with me, we'll get it. Okay, so at this point, we know how to differentiate relations that are defined by expressing one variable explicitly in terms of the other. What I mean by that is that, look, y is by itself on the left solved for, and everything else on the right has to do with x. Y is on the left by itself solved for, everything else is on the right. Okay. Okay. Furthermore, we can figure out how to solve this, right? This is a chain rule where here's the inside and the square root function is the outside. This will be product rule, x times sine of x. Okay. So we know how to do those problems now. And as a matter of fact, if you go through your stock of different kinds of functions, you know how to take the derivative of just about any function you could write down at this point. There's only a couple relations or a couple functions that we haven't talked about yet. So really, you know how to take the derivative of just about any function you can think to write down. That's pretty powerful. Okay, but what we want to do now is talk about relations that cannot be defined explicitly, but rather implicitly. Here's some functions, or I should say some relations. This should say actually relations, such as this is a circle. This is some kind of, I don't know what, some kind of third degree object. But notice that there's no way here to solve explicitly for y. Same thing here. I have a y cubed and a y. It's going to be very, very difficult to figure out how to get all the y's on the left-hand side and solve explicitly. This one I could solve for y, but then I'd be forced to take a square root, so I'd have to have a plus or a minus. So I can't get y by itself. I can't turn it into a function. Neither of these are functions. They don't pass the vertical line test. Okay? So we're going to learn how to deal with this. And really, you know, it's just the chain rule. Okay? So that's all it is. We're going to apply the chain rule to every part of the function. So here's what we're going to do. I know how to take the derivative of x squared. It is 2x. I know how to take the derivative of 25. It's 0. All we have to do is take the derivative of y squared with respect to x. Now, we can take the derivative of y squared with respect to y. It's just 2y. But we're taking the derivative of y squared with respect to another variable. And we know there's a relationship between those two variables. So here's what we have to do. Okay? We're looking for the derivative of y squared. We need to use the chain rule to find that derivative. Here's the chain rule. dy dx equals dy du times du dx. Okay? We can think of y squared as the inside function, sort of as u. Okay? It's kind of a weird way to think about it, but you'll see what I mean. And by the way, for implicit differentiation, we almost always use the Leibniz notation. And here's what it looks like. Let's kind of break this down for a second. The derivative of y squared with respect to x is 2y. Okay, so we look at the outside function as being y squared, basically. Okay, we take the derivative of that and we multiply by the derivative of what's inside. Well, y is what's inside of y squared, right? Maybe I should write this down. Y is inside of y squared. It's kind of a bizarre thing to say, okay? But using the chain rule, the derivative of the whole thing, that's 2y, times the derivative of y with respect to x. Well, that's just dy dx. Okay? So that's how we do it. Okay? So let me put it together now. If I take the derivative of both sides of this equation, I'm going to do it piece by piece by piece. This is an operator. It distributes the same way that anything does. I distribute to the x squared, and I distribute to the y squared. So the derivative of x squared, we know when we're taking the derivative with respect to the variable x, when x is the variable thing that varies, it's just 2x. The derivative of y squared using that chain rule is 2y times dy dx. And the right-hand side is 0. All right, this might look a little spooky at first. Let's see what it says. If I look at a circle, that's my equation of a circle, and I want to find the rate of change of that circle, the rate of change depends on both x and y. Here's the rate of change, dy dx. The slope of that circle, anywhere on the circle, is defined by this expression. Now we can do a little better. We can actually solve for that by subtracting 2x from both sides and dividing both sides by 2y. Okay? Maybe we should investigate this a little bit. Let's take a look at Grapher. Now, what's lovely about this is it can do two variables. So if I'm going to go x squared plus y squared, now your calculator can't do this, but we get a circle of radius 5, and I'm going to zoom out a little bit. There it is, circle of radius 5. That's what that object is. Let's pick a point on that circle. Okay, let's pick a point. Right here. Okay. This is the point 4.5, roughly, comma, was that 3? 2. Okay, so I'm just reading it off the graph. I don't think that's exact, is it? Is that a Pythagorean triple? No. Okay. So let's give it a shot. The slope at this point is going to be defined by negative, was it y over x? So we had. Pardon me, negative x over y. Everyone makes mistakes, right? That means the slope at this point, if I plug in x equals 2 and y equals 4.5, and I make that a negative, okay, the slope of the line tangent to this circle is given by that, which is going to be 4/9, or negative 4/9. Okay, so it's fairly steep. There it is right there. Not too bad, right? Okay, so that's what that means. And the reason the derivative in this case has both an x and a y in it is that I can't ask what the derivative is at x equals 4.5. Because when x equals 4.5, there are two places where y could be. Okay? So I need my derivative to also be defined implicitly. And that will almost always be the case. All right? Okay. So let's do this one now. Now, something I want you to think about when we're doing this. The way this works, you differentiate x normally, okay? In practice, we differentiate x normally. For y, okay, we're going to differentiate as though it were x times dy dx. So we differentiate it in the same way we would do x, okay? But then, when we're done taking that derivative, we also multiply by dy dx. Let's just do it. Okay, we're going to do the derivative of both the left and the right at the same time, and I'm just going to explain this to you. Okay, so we're going to multiply, we're going to take the derivative of x cubed plus the derivative of y cubed equals the derivative of 6xy. Okay, a couple things to notice here. We're going to take the derivative of x cubed. We're going to have to take the derivative of y cubed. And we're going to have to multiply that derivative by dy dx. Over here we got something funny. We actually have a couple functions. Now the 6 won't affect much. The 6 we can just leave in there. But we actually have the function x and the function or I should say the variable x that is varying, and the variable y that is also varying. These are two different functions, so to speak, okay? Which means we need the product rule to do this. Okay, all right, let's look at it. The derivative of x cubed is 3x squared. That one should be pretty straightforward at this point. The derivative of y cubed, we pretend as if it's an x, okay? And that we bring down the 3, power rule, big time. But then we also multiply by dy dx. That's what differentiates these two derivatives from these two. If I take the derivative of x cubed, I'm really actually multiplying the derivative of this by dx, but that's equal to 1. Okay. I take the derivative of y cubed and I multiply by dy dx. Okay, let's look at the right-hand side. So the left-hand side we got now. The right-hand side. All right, so I'm going to take the derivative of 6xy, and like I said, I need to use the product rule. So here's what I did. I took the derivative of the first, which was 6, because the first is 6x, the way I'm reading this. First function, basically. Second function. The derivative of 6x is 6. So the derivative of the first times the second, plus the first, which is plain old 6x, times the derivative of the second. Well, the derivative of y is simply 1 times dy dx, because we take the derivative of things with y's basically the same way we do x's, except that once I'm done taking that derivative, I multiply by dy dx. So the derivative of y is 1 times dy dx. Okay? So now I have this thing where I have a dy dx over here, dy dx over here, but I want to find what the derivative is equal to. I want to have all my dy dx's on the left and everything else on the right. So I've got to collect like terms. Let's put all my things with dy dx on the left. So I subtract 6x dy dx to get that over here. And I subtract 3x squared to get it over here. So I end up with 3y squared, that was on the left already, minus 6x dy dx, that was from the right hand side, equals 6y minus 3x squared. Next step is to factor out dy dx. And I get dy dx times 3y squared minus 6x equals 6y minus 3x squared. Finally, I divide both sides by that quantity on the left, and I get my answer. The derivative of this relation of the y variable with respect to x of this relation is given by this rational expression. Now here's something I want you to keep in mind with these problems. I know it seems like a lot right now, and we're going to do some practice with these, so don't stress about it too much. But there's some things I want to point out. The use here of taking the derivative of y cubed and multiplying by dy dx. Use of the product rule. Whenever I have a term that has both x's and y's in it, I must use the product rule. Okay. The last thing is, once I've taken the derivative of all the terms, I'm not done. I have to solve for dy dx. And sometimes this ends up being the hardest part for people. So, collect like terms. Anything that's got a dy dx attached to it, this one and this one, should go on the left side. Everything else should go on the right side. Okay, we get to this point here, and this is essential. We've got to remember how to factor. Okay, there's not much to factor. I'm just going to factor out the dy dx term here and here. Okay, those go out, and I'm left with dy dx times 3y squared minus 6x, and I'll end up with a rational function. I would say 99% of the time, you should end up with a rational expression. 99% of the time. Okay. There are cases where you won't, but most of the time you will end up with a rational expression. Furthermore, that rational expression you end up with will almost always look very similar in some kind of strange mixed up way top to bottom. Notice how I have 6y minus 3x squared, and then I have 3y squared minus 6x. So I should see in some sense like an opposite relationship between the variables of each. Okay, that's something just to kind of keep in mind. It's not a rule for figuring out what they are, but if your derivative ends up looking like that, you should probably pat yourself on the back. You probably did it at least mostly right. My cat is here clamoring for my attention. All right. And this one I want you guys to practice on your own. Okay. All right. So these are your assignments, so to speak, for this section. Okay. Practice this one. We're going to need product rule here. Okay. Here we're going to need a couple things, right? We're going to need chain rule because I have an inside and an outside. Okay. Oh, that's all I need here. It's a chain rule, inside and outside. The inside, though, has two parts to it. Okay. And then finally, I want you to try taking the derivative of this and evaluating that derivative to find the slope at this point. Okay. Give that a shot. We're going to need to find out what, we already know the point. We just need to find the slope. So to find the slope, I'm going to take the derivative, solve for the derivative, plug this in to find the slope, and then we should be able to find our equation of our tangent line. Okay, there's only one small topic left today, and that is something very mechanical. At this point, I just want to mention to you the concept of higher order derivatives. Okay, this can go along with the chain rule, doesn't have to. Or with implicit differentiation, doesn't have to. So what I have here is I have a function y equals, and I've written it. Just notice that y is also sometimes referred to as f of x. That's fine. The first derivative, you all know how to take that. The notation is f prime if we're talking about the prime notation. And if I want to take a second derivative, d squared y over dx squared is 6x minus x, and that's only the derivative of the first derivative, second derivative. The notation when I use the primes is f prime prime, double prime. Okay, now in physics, in physical applications, the second derivative is very useful and has a lot of meaning. Beyond that, the derivatives in general, in physical applications, don't have as much meaning as the second derivatives. So the first derivative and the second derivative are very important. After that, they get less important. When we talk about higher order derivatives, I just want to mention some notation, which is all this really is. This notation will keep going. This is the third derivative. This is the third derivative here. Once we get past usually about 3 of these, okay, for derivatives we often start seeing this kind of superscript parentheses, and this indicates the fourth derivative. And I think the reason they do that is that there's some disagreement as to whether we should go to Roman numerals after this or just keep on doing the primes. And certainly you don't want to look at the 15th derivatives, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Right? You don't want to do that. Okay, that's kind of silly looking. So instead, the 15th derivative, here we would write as f parentheses superscript 15. That indicates the 15th derivative. Not that you would ever really need that in practice. Okay? And that's it. So the higher order derivatives is just to introduce some notation. Conceptually, there's not a lot to talk about there. All right, everybody. I'll see you in class.